Hello, my dear NEET warriors. Welcome to the second part of Ray Optics in the NCERT line by line series on the Vedantu NEET English channel. And this is your Captain Shreyas. Welcome aboard. And I hope you guys are doing extremely well. And also, make sure that before we start this session, you have marked your attendance. Yes, in our regular classrooms, you have a roll call. So mark your attendance here by smashing the like button. Number two, subscribe to the #1 NEET English channel in the country. Okay. So this is the NCERT line by line series where we decode NCERT properly line by line, and I have completed so many chapters by now. So we are on to ray optics. Last lecture we had started off with the first part where we did reflection and all of that, and we also did refraction at curved surface, and we had just about to start refraction by a lens. That is what we are going to do. All right, so let's begin. Okay, so if you remember correctly, yes, welcome. Hi Disha, hi Sri, hi Bunny, hi Evening Star, Mission. Nice to see all of you. Nice to see suddenly all of you popping up. I was like, okay, are you guys going to wake up or not? But good to see all of you back. Okay, happy morning, Krishna. Thank you for the fire. Sir, can you please start a question practice series for physics because many students like me suffer? Let me tell you, there is a very nice surprise coming up for all of you. The NEET Express has started. See, I'll tell you something right now on our, where is it? NEET English channel. Yeah, already we have started off with something called as the NEET Express. Okay, this is station 0. Okay, so you would have also seen Hope is coming. This particular session is made live, and there is a reason why I made this session live, and something really amazing is going to happen in terms of those students who want to start from scratch, those students who do not have confidence, those students who want revision, those students who want to practice questions. You will see something really amazing coming up in the days to come. This is just the beginning. Station 0 is just the start. And thank you for the massive response. Already the 2 biology classes are over, Baswa sir and Gopika ma'am. Okay, so yes, I have heard you. I know you need question practice. It is coming, but in which format, how, when, everything will be discussed over here. Okay, so 28th November, my dear warriors. I am very good, Krishna. Thank you so much. All right. So, in this particular part, refraction by a lens is something like where you have two refracting surfaces. So, if you talk about something like this, where let's just go to the physics simulations in the FET, and let's see over here. Yep. So this is just a lens. There we go. A lens can either bend the rays by converging, or it can even diverge the rays by pushing them away. This kind of lenses are called as concave lenses. You can see that. You can see these lenses are concave. They are caved in, whereas when they bulge out, that is called as basically convex lens. Okay, so this is a convex when it bulges, and the convex lenses are converging kind of lenses, and concave lenses are usually the diverging kind of lenses. And in these kind of lenses, you will see there are two surfaces where the light will refract. So there are two refractions happening, and that is why this has been kept after the single curved surface refraction discussion. We had discussed this particular formula and this phenomena. So this has been kept after that. So what exactly happens? What's the formula like, and what are the different, magnification formulas, etc. See, let me tell you very clearly over here. When you talk about a lens, let's say for example, this is one surface, this is another surface. This is a structure of a lens, let's say. This is the center, which is also your pole. Okay, this is your center, which is also your pole. And now let's say I divide the lens into two equal halves. That line is then called obviously as the principal axis. Let's say there was an object which is placed over here. Let's say there was an object which is placed over here. So then this will be the object distance or object coordinate or distance. That's how it is called, u. So the rays from that particular object, will enter the lens over here. And at this very particular point, what you will see is that it will get refracted. So how will it get refracted? I need to draw a normal. So if I draw a normal, something like this, maybe this is how the normal will be. Okay, the ray will obviously bend now. Towards the normal because it is entering a denser medium. Now comes the next surface. At that next surface, to see how it bends, again I need to draw another normal over here. Let's say, over here something like this, or I don't know, Chumar just drawing it like this. Okay, great. So this is another normal which is drawn. Okay, and then the light ray, because it is going from dense to rare, it will bend away from the normal maybe, and let's say the ray meets over here. Now this is just one of those rays. Now there will be many more such rays which I can draw at different places. Of course, maybe one more ray here, maybe one more ray somewhere else, and so on and so forth. I'm just showing some few more rays just for your understanding over here. Okay, and maybe it meets over here, then maybe some more rays over here, then maybe, wow, it's like this, let's say, and it's over here. So you can see the rays are meeting over here. So that means this is the location where our image is formed. And then this particular distance is nothing but v, and it is also called as your image distance or image coordinate or image distance. Is that right? Everything is measured from the pole. So that is how ray tracing is done to figure out where the image will be formed because of a lens. And you can see there are two surfaces which are there over here, and the refraction happens at both those surfaces. This particular one over here, this is basically your first surface where the refraction occurs. So this line, the dotted line that I have drawn for that surface, this is basically the center of curvature, number one. And that line becomes the radius of curvature labeled R1. This is the radius of curvature of the first surface where the light rays will refract. Are you able to visualize and understand this? The light rays hit this surface, and over here using Snell's law and the curved surface refraction, it bent. So if I draw a normal, obviously for a circular arc, the perpendicular drawn becomes the radius. This becomes the center of that imaginary circle. So that is the center of curvature 1. This is R1. And this is basically your first surface. This is the second surface, like you can see. This is basically your second surface, like you can see, my dear students. And for this particular surface, when you draw the normal, that also becomes the radius of this particular imaginary circle. So therefore, this will become your center of curvature 2, and this will become your radius of curvature labeled 2. Are these nomenclatures clear in your head? Are these nomenclatures absolutely clear in your head, my dear audience? If this much is clear, then, sir, what is the formula, sir, finally? What is the formula that you get, basically? So the formulas that you get are as follows. The first things first, the 1 by image distance and 1 by object distance is equal to 1 by f was very much similar in the case of a curved mirror, but in the case of a curved mirror, it was a plus. Here, the sign will be different. It will be negative. 1 by image distance, 1 by object distance, negative sign is equal to 1 by the focal length. Yep. That is the first formula, which is also called as your lens formula. This is also called, what is this called? This is also called as your lens formula. Lens formula to locate images. To locate basically an image. You can also check the magnification, which is also the height of the image upon height of the object. This formula, very similar to the mirror formula. Instead of negative v by u, the sign will change. Wherever minus is there, plus will come. If plus is there, minus will come. So this will be plus v by u. That's the major difference. So this is basically your magnification. This is nothing but your magnification formula. This is magnification formula. The same theory which we have learned before is still applicable here also. So, for example, if magnification is positive, that means the image is going to be erect. And if the magnification is going to be negative, if the magnification is going to be negative, that means the image is going to be inverted. It is going to be upside down. That's the sign of the magnification, which will come depending on the sign of V and U. Remember, V, U are sign sensitive. Yep, they are sign sensitive. So you have to use your sign convention. And we have seen how the sign convention works. Yep, wherever the incident rays are moving, that side of that lens or the mirror becomes positive. So that means this side obviously will become the positive side. This will become the positive side, and obviously then this side will become the negative side. This is as per the sign convention. So remember this sign convention as before. Sign convention is as before. Okay, as before. So always incident direction is considered as positive, and upward direction is also considered as positive. Anything on the top is positive, anything below is considered negative. No, they will not ask you derivations in the exam. Sri Lakshmi, I'm not sure how long will the session go. Sir, but there is one problem, sir. You'll be like, what? Sir, in mirrors, F was related to the radius. What was the formula? Come on, put it up in the chat box. What was the relation between radius of curvature and the focal length of a curved mirror? R and F. F focal point was the midpoint of center and the pole. So R was 2 times the focal length. Remember that? Yep, correct. Hi Suparna, good morning. Yes. Here, is R going to be 2 times of F? No. First of all, there are 2 radius. There are 2 surfaces. So there are 2 radius of curvature. Oh, number 1. Number 2, I think it will also depend on what is filled inside. That means the refractive index of this particular lens. Yes, the refractive index of this particular lens will also matter. That means mu, the value of mu relative to the relative refractive index of the lens with respect to the medium outside, whether the lens is kept in water, glycerin, kerosene, petrol, alcohol, some other liquid, who knows. So the relative refractive index, because the light rays will bend accordingly, so that will also matter. So the actual formula for the focal length comes out like this: 1 by the focal length of the lens is refractive index of the lens with respect to the outside medium minus 1, the whole thing, into 1 by R1 minus 1 by R2. This is the formula. If you're wondering what is this is relative refractive index. So this is the refractive index of the lens by refractive index of the medium. If the medium is air, then this mu m will be just 1. So you will just put the absolute refractive index of the lens. If the refractive index is air of outside medium, the refractive index of outside medium, if it is air, it will be 1. So anything by 1 will be that anything. So you can just put that absolute refractive index. If it is glass, put directly over here 1.5. That's how it works. R1, R2, you have to follow the sign convention. R1, R2, you have to follow the sign convention. So this is the formula, and if you are wondering what it is called, well, it is called as the lens maker's formula. The lens maker's formula. Why? If somebody has to design a lens of a particular focal length, and if they know what material they are getting, or if they have a choice of material, they can select mu R1 and R2 to design a lens of a particular focal length. So that's why it is also called the lens maker's formula. Got it? Very good. Awesomeness. Let's try to do a simple question on this so that you get an idea. Let's see what kind of question they have kept. Okay. Okay, this is different. Okay, wait a minute. This is different. No, we'll do separate examples so that we can build the concept. Let's build the concept, my dear warriors. Let's say I have a concave lens. This is, let's say, 10 centimeter. This is, let's say, 5 centimeter. This is having a refractive index of 1.5. Can you find the focal length? Can you find the focal length of this particular lens? Let's try to figure this out. It's not that difficult. So in order to find the focal length, the formula that we have is 1 by f is equal to mu lens refractive index with respect to the medium minus 1 by r1 minus 1 by r2. Okay, fine, sir. What is the refractive index of the outside medium? It is air. If outside medium is air, the refractive index of air is just 1. This will just become 1.5. You can just divide it by 1. It won't make a difference. Okay. Now, what is this R1 and what is this R2? Be very, very careful. See, light rays will go here. So, wherever that light rays go, that side becomes the positive side, and the exact opposite side becomes the negative side. Now, you need to understand who is R1, who is R2. For that, you should know who is the first surface, who is the second surface. If the light rays are coming from here, this is the first surface. So, therefore, this would be center of curvature 1 and this would be R1. If light rays enter this surface next, so this would be the second center of curvature. That means the second radius of curvature will be 5 centimeters. Got it? How light hits the surface? In that order, you will label them surface 1 and surface 2. Accordingly, for that surface, that radius 1 and center 1, that radius 2 and that guy's center number 2. Yes. Yeah, we'll come to example 9.7, everything. Hold on. Okay. Now check this out. R1, should it be positive or negative? Well, it is on the negative side. So that's why it will be negative 10. R2, it is on the positive side. That's why it will be plus 5. That is how the sign convention will work. So therefore, what I will write, 1 by f is equal to 1.5 minus 1 is basically 0.5. Okay. This is negative and negative, both negatives together. I will take that negative sign common. So it will be 1 by 10 plus 1 by 5, which can be written down with LCM as 10, 1 plus 2 by 10, which is basically 3 by 10. 3 by 10 over here. 0.5 is nothing but half. 0.5 is nothing but half. Okay, so this will just become minus 3 by 20, that is 1 by f. So the focal length is negative 20 by 3. Focal length is negative 20 by 3 centimeters. That is the answer. Everybody understood? Is this absolutely clear? Yes, that's how the sign convention is. Correct. Yes, definitely, Sukanya. Some question problem solving series with PYQs, everything is coming. Now, the meaning of the word negative is that for this particular lens, which is there, if the rays were like this, parallelly incident, they will obviously diverge. They will obviously diverge. If one extends them backwards, they will meet here. This particular distance is basically 20 by 3 centimeter in absolute terms. So that is why the focal length is negative, because this side is always negative and this side will be the positive side. So for concave lens diverging in nature, the focal lengths are negative. I hope this is absolutely clear. We will do one more example so that you guys get a hang of it. Imagine you have been given something like a lens like this. Okay, a lens like this. It's a plano-convex lens, and it has been told to you this is basically 20 centimeters. This is, let's say, for example, having a refractive index of uh, 1.6 or something, and the outside medium, the medium outside has a refractive index of 1.2. Okay, so there is a refractive index. Then you have placed an object over here. You have placed an object over here at a distance of 40 centimeters. At a distance of 40 centimeters. The questions are as follows. Find what is the focal length. What is the focal length? Number two, the image nature and characteristics, where it is formed, how it is formed, what is the magnification, is it inverted, is it erect, enlarged, all these things. That's what we are trying to figure out. Okay. Yes, no issues. Harish, I will anyways not be doing NCERT for modern physics, because doing NCERT for modern physics doesn't make sense also, because it is anyways a little bit theoretical, postulates, all those things are there. And from the NEET perspective, I think we have to approach it in a completely different way. So anyways, wave optics will be my last class for NCERT line by line series. That would be next week. After that, modern physics, whenever I do it in a different way, I will approach it differently. Okay, and we will cover it up. Anyways, you can watch my Super 6 classes also, my last year classes, in case you want it. But if you can wait for some time, that would be really great as well. Okay, so shall we do this particular question, my dear warriors? Okay, let's do this. It's a plano-convex lens. Keep that in mind. Oh, for a plano-convex lens, you have to be a little bit more careful, because see what will happen. I'll tell you. This is the first surface. This is the second surface. For the second surface, this is the radius. This is the center of curvature. So the radius of curvature number 2 is this. But for the first surface, where is the radius? Where is the center? Because it is not even curved. So what should you take? Let me tell you that when something is curved more, the radius is less. As it curves less, the radius becomes more. And when something becomes flat, the radius becomes infinity. Infinitely large, because now this circle is big, this circle was small, even big circle, this will be infinitely large circle. Infinitely large circle means the radius of curvature is infinity. So that means the radius of curvature number 1 is infinity. You cannot locate its center. It's one of the biggest circles ever, because flat surface has infinite radius. Got it? This concept has to be entering, it should be there in your head. Okay, fine, sir. So, sir, what is the focal length answer, sir? Let's find out. It is mu minus 1 by R1 minus 1 by R2. Okay, 1 by F. Okay, sir, but we need our sign conventions. Yes, sorted. Okay, so this is the positive side, perfecto. and this, obviously everything on this side, oops, everything on this side is negative. Oh my god, this is negative. Okay, fair enough. So what is the refractive index of the lens with respect to the medium? Refractive index of the lens 1.6 upon refractive index of the medium 1.2 minus 1. Okay, 1 by radius 1. Radius 1 is infinity minus 1 by radius number 2. Second surface's radius is 20, but will it be positive or negative? That radius is on the negative side, so it should be minus 20. This is the catch. Be careful about the sign conventions. Everybody fine till this point? Okay. So what is next? Let's find out. 1 by f is equal to 1.6 by 1.2 is 16 by 12. 16 and 12 both are divisible by 4. 16 goes with 4 times. 12 goes with 4 3 times minus 1. What is 1 by infinity? See, when you divide it with a large number, the answer becomes small. When you divide it with the largest number, the answer will become the smallest. So 1 by infinitely large, the answer will be tending towards 0. So you can put 0 over here. Minus minus becomes plus. So plus 1 by 20. Okay, sir. So 1 by f is equal to 4 by 3 minus 1 will just become 1 by 3 over here, and this will just become 1 by 20 over here. So therefore f will become 3 multiplied by 20, or f will just become 60 centimeters. The focal length will just come out to be 60 centimeters. First job has been done. We had to figure out what is the focal length. That job has been absolutely done. Now the next job, we'll figure out where the image is going to be formed. 1 by v minus 1 by u is equal to 1 by f. What is image distance? I don't know. What is object distance? It's clearly mentioned. It is 40 centimeters, but it is on the negative side. So minus 40. 1 by f, 1 by 60. Okay. So 1 by v is equal to minus minus is plus. So when it goes on the other side, again it will become minus. Take the LCM of 60 and 40, that is 120. 60 goes with 122 times, 40 goes basically 3 times. 2 minus 3 is negative 1 by 120. Therefore, V will be negative 120 centimeters, number 1. Next, let's also find the magnification. Magnification is V by U. V is minus 120. U is a negative 40. So basically negative cancels, and we will get it as 3 units. We'll get it basically as 3 units. From this, what do we conclude? The image is first of all on the negative side, means it is over here. This side will be virtual. This side, because the rays can converge, will be real. So image is virtual at 120 centimeters from the lens. Not just that, you can see the magnification is positive. That means it is erect, it is not inverted. And it is 3, that means it has been magnified, or it has been also enlarged in nature. So you will see an enlarged image, erect image, as well as virtual image because of this particular setup. Yes, definitely it is useful for your board exam. Why else will I do this? Okay, fair enough. How to solve these questions? Right. Now, the last thing which we have to deal over here. Okay. All this is done. This is done. This is done. Last thing. Remember, so all these things, let me just mark it over here, whatever we have just done. So refraction by lens. Okay. So here the first refracting surface forms an image 1 from the object. The image 1 acts as an object for the other surface that forms the final image. So using these formulas, we basically get this. 1 by v is equal minus 1 by u is equal to 1 by f, and also these are the rules used for ray tracing. like a ray which is parallel to the principal axis after refraction passes through the focus. A ray which passes through the center of the lens emerges without any deviation. A ray which passes through the first focus will emerge parallel to the focus. A ray which is parallel, similarly, a ray of light which is incident on the concave lens appearing to meet on the principal axis on the second emerges parallel. So these are the rules used for ray tracing, just like we used it for mirrors as well. I'll just explain this to you. If a ray is parallel to the principal axis, what will happen? It will pass through the focus. That's it. Simple. But remember one thing, that in case of a lens, usually we have two kinds of focus, the actual focus and a point similar to the focus on the other side. Okay, instead of light coming from here, if the light went from here, where would the light meet? It would meet here. So that is also called as the second focus. So that's why you will see usually this term that the focus is where the light will actually meet, and you also have it on the other side called as the secondary focus. So there are two focuses usually for the lenses. Okay, if a light passes through the focus which is secondary, then it will become parallel. It makes sense, because if the light came parallel from here, then it would pass from the focus over here. That also makes sense. Reversibility principle. Last thing is, if the light passes through the center of this particular lens, then it will pass as it is without getting deviated. The same things are also true for a concave lens. So if a light passes through the center, it will definitely pass undeviated. It will not deviate at all. If a light is parallel, it will deviate in such a way that when you extend it, it will appear to diverge from the original focus, and the secondary focus is this point over here. So if a light is incident towards the secondary focus, it will become parallel. It makes sense, because if light were to come from here, then it will diverge like this, and it will appear to diverge from the focal point. So these are the rules used for ray tracing. These are the rules used for ray tracing. Not much useful for NEET perspective, but I have just told it to you. These were things which you have learned back in the 10th standard. This was the magnification formula. And remember, you have to apply the sign convention that for erect, M is positive, and for inverted, the M is negative. We have already discussed that, all these things. Last things over here, before we go ahead, power of a lens. Power of a lens, the formula goes like this. It is 1 by F. Yep, it is 1 by F. Now, what is the meaning of power? Power is nothing but it is a measure of how much does it converge or diverge. So when you have a convex lens, the rays converge. When you have a concave lens, the rays diverge. So how much is the convergingness or divergingness? That is decided by the power. So imagine if the rays of light meet over here versus the rays of light meet over here. This has less focal length, this has more focal length. Because it is converging earlier, it has more power. Here it is converging later, so it has less power. So that is why it is reciprocal. If the focal length is less, the power is more. If the focal length is more, the power is going to be less. Got it, my dear warriors? Why it is 1 by F? More focal length, it will have definitely less power. Is this absolutely clear, everyone, till this particular point? Okay. Now, also remember, the power can be positive or negative. If the rays converge, then it is positive. If the rays diverge, then the power is going to be negative. That is also something which you should keep in mind. So I think all these pointers will be mentioned over here. Yep, let's see that. So basically, yes, the power of a lens is positive for a converging lens, whereas it is negative for a diverging lens. Also, what is the unit of power? What is the unit of power? The unit of power is basically diopter, and only when the focal length is in meters. If it is in centimeters, please convert it into meters. Convert it into meters before measuring that power. Example, if the focal length is 40 centimeters, if the focal length is 40 centimeters, the power will become 2.5 diopters, because 40 centimeters is 0.4 meter. So which means 1 by 0.4, which is nothing but 4 by 10, which is nothing but 5 by 2, which is nothing but 2.5. So 2.5 diopters will be the power of the lens. And because the focal length was positive, the power is also positive. If the power is positive, that means it is converging type of lens, more like a convex lens. Is this clear? Hostel facility, I think, is available through our contacts, not directly, but we have some kind of tie-ups. So if you are a NEET repeater, you can definitely visit the Vedantu Learning Center in Chennai or Madurai or wherever you are, and try to connect with the counseling staff. They will help you with the accommodation as well. Yep, if you're especially NEET repeater. Okay, so a magician during a show makes a glass lens with some refractive index of 1.47 disappear in a trough of liquid. What is the refractive index of the liquid? Could the liquid be water? Now, you might have seen this. A magician during a show makes a glass lens with some disappear in a liquid. So imagine there is a lens over here and you have a beaker or something like this over here, and what happens is you pour some liquid into this. You pour some liquid into this, and as soon as you pour some liquid, this lens should basically disappear. How will that happen? This can only happen in one particular scenario, if the refractive indices basically have to match. Then you will not see any blurriness or any kind of deviation or any kind of distortions when the light rays will enter and exit through the lens and the medium. If the refractive indices were different, then the rays will get distorted and you will feel, okay, something is wrong over here. Imagine something of the same refractive index, the light won't bend. So there is no way you can tell that something actually is there. Your eyes will be deceived. So that is the reason why you will make sure that the refractive index is very much similar to that of the outside medium, and that's how you can make it disappear. Is the liquid water? No. In fact, usually it is glycerine, because the lens refractive index and the glycerine's refractive index are roughly similar, because 1.47 is roughly also the refractive index of glycerine. Is that okay? So that is the trick which is used. Example 9.7. In this, the focal length of 0.5 meter. What is the power of the lens? Very straightforward, guys. Power is 1 by f. Power is nothing but 1 by f. So 1 by 0.5, which means it is 2 diopters. Yes, it is 2 diopters. Perfect. So this is definitely done. Next, the radius of curvature of a convex lens are 10 centimeter and 15. Focal length is 12. What is the refractive index? So you know the focal length, you don't know the refractive index. Exact opposite. So use 1 by f is refractive index minus 1, 1 by r1 minus 1 by r2. But you have to make sure that the sign convention is also followed properly. So if this is the convex lens, this is the this is the second radius, because this will be the second surface. This is the first surface. So the center of curvature 1 will be here, and the radius of curvature r basically what? 10 centimeters, and how much? 15 centimeters. Yes, this is 15 centimeters. This is the negative side. This is the positive side. So 1 by focal length. What is the focal length? Focal length is 12. So 1 by 12 is refractive index minus 1. 1 by R1. What is R1? Plus 10. Minus 1 by R2. What is R2? It's not 15. It's on the negative side. So minus 15. Solve this. You will get N as, or the refractive index as, 1.5. Understood how to solve this particular question? Solved example. In-text questions are very important. Okay, very good. Awesomeness. For a glass lens in air, okay, now, so that was the second part of it. That was the second part of it. If that convex lens has 20 centimeters focal length in air, what will be the focal length in water? Okay, so how to do this particular question? If a convex lens has 20 focal length in air, how much focal length will be in water? Water's refractive index is given. See, 1 by F is mu minus 1 by R1 minus 1 by R2. When you change the outside medium, this particular part will always remain a constant. Only thing that will change is this. So therefore, 1 by focal length in air upon 1 by focal length in water, what you will do, this will be refractive index of the lens in air. So refractive index basically just of the lens in air minus 1. Here inside water, it is the refractive index of the lens with respect to the water minus 1. That's the major difference. So focal length of water by focal length in air is equal to refractive index of the lens. What is the refractive index of the lens? Yes, it is 1.5. It's a glass refractive index. And refractive index of water is 1.33, which is 4 by 3. So you can write it as 1.5 divided by 4 by 3 minus 1. Okay. In air, what was the refractive index? It was 20. So focal length in water by 20 is equal to 1.5 minus 1 is 0.5. 0.5 is 1 by 2. 1.5 is 3 by 2. 3 3s are 9. 2 4s are 8 minus 1, which is 1 by 2. 9 minus 8 is 1. 1 by 8. So that will be basically 8 by 2, which is basically 4. Okay. So focal length in water is 20 multiplied by 4, which is 80 centimeters. So around that is what you are going to get. Here they have used 1.33. They have not used 4 by 3. That's why they have got it as 78.2. But our answer is very much close to 78.2. So that's how you do the third question. Is this clear? How to solve this example? Yeah. Noted, Jagannath. All right. Moving on to the next concept of combination of lenses. Imagine two or more lenses are touching each other. When two or more lenses are touching each other, we cannot do this. We'll use the first lens, find where the image is, then again make that image as the object for the next lens and find where the image is, then make that image as the object for the next lens and find where the image is. It will be a repetitive process. I don't want to do that. Instead, can we combine all the lenses into one single lens when multiple lenses are in contact? Yeah, so that is very, very important. So when you have several thin lenses of focal length f1, f2, f3 and they are in contact, both the words are important. Several thin lenses are in contact. Why this word is important is because there was a question once like this which said there is a convex lens. Let's say the focal length of that particular convex lens is plus, I don't know, 25 centimeters. And then there is a concave lens of, let's say, focal length minus 10 centimeters. And it was given that if a parallel beam of light, they are not in contact by the way, if a parallel beam of light enters here, it exits also parallelly. So if that is the situation, can you figure out what is that? Can you figure out what is the distance between the lenses? Can you figure out what is the distance between the lenses? This was one of the questions. And this is asked in multiple competitive examinations. Now over here, obviously the lenses are not in contact. Obviously the lenses are not in contact. The lenses are not in contact. So how do you do such a question? I'll tell you what, it's a very straightforward trick over here. Think like this. After the first refraction from the convex lens, because the rays are parallel, they will definitely meet. Where will they meet? They will meet at the focal point. But since I want the rays to be parallel after concave lens, what if I ask these rays to meet at the focal point of the concave lens? Just imagine this. Right now, this particular distance is 25 centimeters. They are trying to meet over here. But I ask it to meet at such a point by placing the concave lens, which also becomes the focal point of the concave lens. We know the rule. What happens? If the rays are meeting towards the focus for a concave lens, they will end up being parallel. So you can see the rays will become parallel. Actually speaking, they won't even actually reach till there. So I should ideally show this as dotted lines. Yes, I should ideally show this as dotted lines. That's what will happen, which means this particular distance, which you can see right over here, this one, yep, that is the focal length of the concave lens, which is nothing but 10 centimeters. So if this is 10, this is 25. Can't we just figure out how much this distance will be now? Yep, this is going to be 25 minus 10. So it will be 25 minus 10, which means it will be 15 centimeters. That is the answer. So this is the correct answer for this particular question. The lenses were not in contact. Is this okay? All right. So coming back over here, in this, the essential criteria is the lenses are thin. Yes, that's anyways the criteria, but they are also in contact. So all lenses, multiple lenses, you can convert it into a single lens of effective focal length and effective power also. What's the formula? Always the powers get added, the focal length reciprocals get added. So the net power is P1 plus P2 plus P3, whereas the focal lengths get added like resistors in parallel. So P is P1 plus P2 plus P3, 1 by F is 1 by F1 plus 1 by F2 plus 1 by F3. That is what it is. Okay, so that is again very important here. P is the net power of the lens combination. Okay, and individual powers may be positive and even negative, so be careful about that. So some of the terms on the right hand side may be positive, like say for convex lenses, and some of the negative terms might be there for concave lenses. Okay, also the last thing, the net magnification, because each lens will try to magnify, may try to zoom it in. So the net magnification is given by the product of all the magnifications, m1 into m2 into m3 into m4, like that. So that is how you get the net magnification. So the total magnification m of the combination is a product of all the magnifications of individual lenses. That is something which you should keep in mind. Let's have a look at the question which is there on this. Find the position of the image which is formed over here in this particular question. But the funny part is, these lenses might be thin, but they are not in contact. These lenses might be thin, but they are not in contact. So the funny part is, you cannot use this particular formula at all. If you had to use this formula, it had to be a question like this. Let's say there is a lens here, there is a lens here like this. Let's say the focal length is 20 centimeters. The next focal length is, let's say, minus 40 centimeters. Okay, can you find the effective power of both the lenses? Let's say this was the question. I will be like, yes, definitely. Since both these lenses have different focal length and I can combine them into one singular lens. First of all, 1 by F effective is 1 by F1 plus 1 by F2. So what is F1? F1 is 20. What is F2? It is minus 40. So it will be 1 by, or basically LCM I can take it as 40. So it will be 40 over here. This will become 2 minus 1. 2 minus 1 is just 1. So it will just become 1 by 40. That is 1 by F effective. You can also write this as effective focal length is just 40 centimeters, which is 0.4 meter. but I want effective power, which will be 1 by F effective, which is 1 by 0.4, which is 1 by 4 uh, by 10. So 10 by 4 is nothing but 5 by 2, which is 2.5 diopters. So the effective power is 2.5 diopters. Correct. So that is the effective power of the lens. This can be used if the lenses are in contact. But in the NCERT solved example in text question, the lenses are not in contact. You can see there is a gap of 5 centimeters from 10 centimeters between the lenses. So what you do is you take the first lens, object distance as 30 with negative sign, find where the image is. See, they have used lens formula. 1 by V minus 1 by U is 1 by F. Focal length is given to be 10. Object distance negative 30. They found the image to be at 15 centimeters. And that is coming out 15 from the first lens. So from the first lens, if it is at 15 centimeters, for the in-between lens, because already the gap between both of them, is 5. Oops. The gap between both of them is 5, which means actual distance from the second lens will be 15 minus 5, which is 10 centimeters. So for the next lens, what will happen? The image of the first lens will now become the object for the second lens. And that object will be not at 15, it will be at 10 centimeters because of this 5 centimeters gap. So that is what you will see will be done in the next part. You can see object distance is 10, the focal length is negative 10, 1 by V minus 1 by U is 1 by F. Surprisingly, what happens is the answer for that comes out to be as infinity. Now, the moment the answer comes out as infinity, don't get scared. It means the rays have just become parallel. It just means the rays have just become parallel. The image is not formed. Yes, the rays are not meeting. That's why you can say the rays have become parallel. If the rays become parallel and they pass through a convex lens, what will happen? They will definitely meet at the focal point. And the focal length is 30. So they will definitely meet at 30 centimeters, like you can see. So that's why the final image will be formed at 30 centimeters from the last lens. But if you actually measure it from the object, this 30, this 5, this 10, and this 30, all of them to be added. So 30 plus 5, 35 plus 10, 45, 45 plus 30, that is going to be 75. So 75 centimeters from the object, that's where the final image will be formed. That's how you solve this particular question. Is that okay? Shall we go ahead? All right. So we are coming towards the prism part now. We are coming towards the prism. Let's get ready. I think we might have the prism simulations. By the way, you should play around with this a lot. You will get a feeling of how the lenses magnification, everything works. When the object is far, you can see the image is highly diminished. It's formed near the focus. As you bring it closer and closer and closer, the image becomes enlarged slowly, but it is still smaller than the original object. But it is inverted until you make it go towards the focus. Once you go towards the focus, you will see that's it. It is not formed because the rays will become parallel. After this point, I'm not able to change it. After this point is where the image will be enlarged. As you can see, there is a virtual enlarged image of that particular, pencil which is formed over here. This is virtual. This was real because the rays are meeting at this point. That is what happens for a convex lens. For a concave lens, the image is always diminished over here in front and it is erect, even though you bring it here. Yes, you can see it is diminished, erect image, and it is also virtual in nature. That means you will have to see from here. You will see this object over here. You will see a small object's image over here. Yeah. Whereas if you use a convex lens, you will not be able to see it unless this is over here. You will see, if you see using this lens, you will see a big image of this particular object. Okay. I hope this is absolutely clear. Which part, Shri? Which part you want? Let me know. Now let's talk about lenses. What do you say? Prisms as well. Let's come to prism. I think prism was also there, but where did prism go? Mm-hmm. Over here. Yes. Okay. So finally, we have come to prism. Now, what's a prism? Prism, lot of people think it should be triangular. No. A prism means you have two surfaces which are at an angle to each other. Imagine there is one surface here, there is another surface here. They are parallel. Then it becomes like a normal glass slab. But if the surfaces are like this, like this, like this, like this, like this, something making an angle, that object is called as a prism. Basically, two surfaces refraction, flat surfaces, but at an angle. Yeah, all right. So, as you can see over here, my dear students, imagine this light which was normally going over here. If I introduce a glass kind of prism over here, you can see the light will bend so beautifully, and it has refracted here as well as here. I can also make that light fall at different places, in fact even at different angles as well. Let me just turn it. Yep, I can make this go like this at different angles, and it will definitely deviate and bend also by different amounts. I can also turn the prism, and you will see that if the angles change, you will see that even the refracted ray which emerges out also will definitely change. We can also have a beam of light to see how exactly it goes to get a more clearer picture. So if I change this, you can see how the light rays will, bend when different angles of incidences are there. Or I can even change this over here beautifully. Correct? So that's what basically a prism is. Now, instead of this, if I use this, that is also a prism, because you still have two surfaces. Even if the top is missing, don't worry, it is still going to be a prism. But if I use this is not a prism, because both the surfaces are parallel. This is a slab. You will see that the ray of light, you will see that the ray of light which is there, it is coming out parallelly. No matter what you do, no matter what you do, the ray of light will always come out parallelly. But it's only the case of the prism where the ray of light is not parallel to the incident, it is at an angle, it emerges at an angle. So that's why we study prisms differently. So this is also a beautiful exercise. This is just a lens. Okay, this is not a prism, of course. So you can also have multiple prisms combination. So if you have two prisms like this, then you can see it will be deviated multiple times. I can also make it go opposite like this. You can see it deviated here, and again it went there. So you can keep as many prisms as possible, and you can make the light go whichever way you want by arranging these prisms at different angles, and you can deviate how much ever you want them to be. So that is beautiful application of prisms, and it is used in your camera lenses and all of that. Okay, I hope this is clear, my dear students. Okay, 9.6, which part of 9.6? Sorry, you said 9.8, my bad. In 9.8, see, I just told, I don't know whether you're able to see those lenses. There is one lens over here. This is the object number 1 that is forming the image over here by lens formula at 15 centimeters. That image for the next lens which is there becomes the object, because there is a gap of 5 centimeters from that lens. The object's distance will be 10 centimeters. So object distance is 10 centimeters. And using lens formula again, the image came out to be at infinity. So the final image due to this middle lens I2 is basically at infinity, meaning the rays of light are just simply parallel. And whenever rays of light are parallel, then what happens? They will converge or diverge depending on the type of the lens. So for the third lens, which was convex in nature, the rays basically just met at this particular point, which is the focal point, which definitely will be 30 centimeters, which will be 30 centimeters. So that's why the final image is formed at 30 centimeters. You just have to use the lens formula multiple times for each of the lenses. Is that okay? Thank you for all the fire, Krishna and Disha. Thank you so much. Now, the formulas that you should know and the terminologies that you should know for a lens. Number one, the angle between the refracting surfaces is A, which is also called as the prism angle or the angle of prism or the refracting angle of the prism. I think it will be mentioned somewhere. Maybe not here. Okay, it's not mentioned. Anyways, no issues. I'm glad MC you understood. Hi sir, I'm new to the class. My name is Lalita Priya. Welcome Lalita. I hope you are enjoying the class and loving those simulations as well as understanding all these examples and theory as well. Keep it up and stay subscribed and keep watching all the videos. And also we are starting off with station 0 of your NEET Express, and something really big is going to happen in the NEET Express as well. Okay. Now, this is your incident ray. It refracts and refracts. This is called incident ray. The ray which finally comes out is called emergent ray. There are some angles which are marked over here. This is the angle of incidence I. The final angle by which it comes out, this is emergent angle. You can see E is the symbol used for that. Internally, when you draw the normals, there will be some angles which will be formed by those rays. With the normals, they are called R1 and R2, as you can see over here. Okay, R1 and R2. This particular ray will deviate by some angle, meaning the ray was supposed to go here, but it ended up going here. So if you extend it backwards, this is the angle by which it has deviated. The symbol for that is delta, as you can see over here. So what's the relation between this deviation and the other angles? First important relationship, delta is I plus E minus A. Angle of deviation is incident angle plus emergent angle minus the angle of prism. This is the first relationship. Hello Arni, welcome. Welcome. A lot of people new to the class. Nice to know all of you. Some of the people forget to mention, sir, I'm new. It's good that you're telling me that, sir, I'm new. Yep. That way I will know you. Yeah, or else you will go unnoticed. So this is the relation between incident angle, emergent angle, angle of prism, and the deviation angle. That means coming back over here, let's get rid of these things. I don't want it. So as you can see over here, can I draw normals? Yes, I can draw normals. Do you see over here that this angle, can I zoom into this? No, I can't. This angle is the incident angle. This angle is the emergent angle. If you see, the ray was going like this, but it ended up going like this. So this is the deviation. This is the angle of the prism. That's the terminologies which have been used. Next important point, which is not mentioned here, but I will give it to you right over here. The internal angles which are there, R1 and R2, if you add them, guess what? You will get the angle of prism. You will also get the angle of prism. So R1 plus R2 is another important relationship that everybody must know. Yeah. Welcome aboard. Welcome aboard, Thinasari. Yes, all the new Pandus and Champas to the class. Okay. Now, there is a interesting thing that happens. If you see, this is our prism. I can't do anything with it. Okay. I just wanted to make it a little bit bigger, but unfortunately, I can't make it big. It's okay. Now, what I will do is, I will make the light fall at different angles and I will see how much it is deviating by. So let's say right now, as you can see, the angle of incidence is very large. Can you see? It's like 85, 90 degrees almost. From the normal, if you measure the incident angle, it is very large. So it is deviating this much. Now, if I make the light fall, my goodness, almost like this, it is almost getting internally reflected. So not all the angles are permissible. So as you can see over here, as I change the angle of incidence, the deviation also will change. The deviation also, how much does it deviate by also changes. Now, to better understand deviation, I will better rotate the prism because then it becomes very obvious. Rather than rotating this, I will rotate this. It's one and the same thing. I rotate the prism or I rotate the torch, one and the same thing. Okay. The ray was supposed to go like this. How much is it deviating by? See, earlier it deviated so much. Now it deviated less, 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 less. Now more. Do you see that the deviation was maximum then or a large value earlier? Then it became less. And then again it started increasing, which means for different angles of incidence, deviation is different. But for a particular angle of incidence, the deviation, see, now it is minimum. It is minimum because after this it increases. So over here, I think it was minimum. The deviation is the least here because after this it increases. So if one draws the graph of deviation with an angle of incidence, it looks something like this. Is it now making sense to all of you? Why it is looking like this? Why it is looking like this? It is becoming minimum for some particular angle over here. Watch it once more. Watch it once more. See, it is deviating by a large amount. Now the deviation decreased, minimum, and again became more. So that is why it decreased and became more as the angle of incidence has changed. So when the deviation is minimum, as you can see, this is when it is probably minimum over here. Then a peculiar thing happens. I'm not sure whether you're able to see this very clearly. This angle and this angle, the incident angle and the emergent angle, both are going to be equal in amount. Both are going to be equal in amount. Correct. Yes, both are going to be equal in amount. And that is what happens. So when the deviation is minimum, then the incident angle is equal to the emergent angle, number one. Even R1 will be equal to R2. That is also second thing. That means the internal angles are also going to be equal. Everything is going to be symmetric. Symmetry will be there. Symmetry will be there on both sides. Even the ray inside will be parallel. Even the ray inside is parallel to the base. Can you see that? The ray inside is parallel to the base. Everything is symmetric. So the ray inside is parallel to the base of the prism. Is parallel to the base of the prism. Everything is going to be symmetric. And when that happens, that minimum deviation formula comes out as this. Mu is equal to sine of A plus delta minimum by 2 by sine of A by 2. Very crucial, important formula. Refractive index is sine of angle of prism plus delta by 2 by sine of angle of prism by 2. This is the formula. But if the angle of prism itself is very small, thin prism, this prism is large prism, big prism, thin prism. 2-3 degrees is the angle of prism. Then you can do some approximations, small angle approximations. So for thin prisms, very, very important, when you have a thin prism, then the deviation approximately becomes, refractive index minus 1 into A. Very, very important. Refractive mu minus 1 into A. Basically, this graph which is there, which is shown right over here, this is usually true for large values of A, angle of prism. But the moment you have a thin prism, you will see this particular graph just becomes like this. In fact, the deviation is not even going to be too much. It will not be so high also. It will be somewhere over here. So you will see this is how the graph will look like. The minimum deviation and any other deviation is approximately the same. Delta is approximately, delta minimum is small and same throughout. What is this for? This is basically for thin prisms only. This is basically for thin prisms. It is not so curved. The curve becomes very, very flat. It is not much deviating for many angles. That is the difference when it is a thin prism. So that is something which you are supposed to know. Now, they are not given any questions over here, but if at all there was a question, how could it be framed? Let's say it is given to you. Let's say it is given to you, my dear students, that you have an equilateral prism, with a deviation of 30 degrees for incidence of 45, or let's say 40 degrees. Find the emergence angle. Find the emergence angle. How do we do this particular question? This is very straightforward question. First of all, let's see what and all is given. Equilateral prism means angle of prism is 60 degrees. Deviation clearly given to be 30 degrees. Incidence, that means I, is also given to be 40 degrees. Emergence angle, that is asked. Is there a relationship between all of them? Definitely there is. Remember, deviation is I plus E minus A. I plus E minus A, that is the formula. So delta is I plus E minus A. Therefore, E is equal to, or take E over here. So it will be delta minus I plus A. So what is the deviation? Deviation is 30. What is incident angle? That is 40. What is angle of prism? Well, that is basically 60. So 30 minus 40 minus 10. Minus 10 plus 60, that is going to be 50 degrees. So emergent angle is 50 degrees, as you can see. Is this going to be minimum deviation? No. This is not minimum deviation, as I is not equal to E. Emergent angle and incident angle are not equal, hence they are definitely not going to be minimum deviation. Let's say another example we have. And it says that you have an angle of prism given to be 30 degrees, and you have the deviation which is minimum, and that is also given to you. Let's say that is maybe 60 degrees. Question is, find refractive index, incident angle, emergent angle. Can you do this? Yep, definitely we can. We can definitely try doing this. First of all, To solve for refractive index, let's use this formula right over here. Refractive angle of prism is big, so for large angles use this formula, sine a plus delta by 2 by sine a by 2. This is the formula which has been given to you. Okay, so refractive index is sine of a plus the minimum deviation by 2 by sine of a by 2. Okay, sir. So what is the angle of prism? It is given to be 30 degrees. What is the minimum deviation? It is given to be 60 degrees. Whole thing divided by 2. Whole thing divided by sine of angle of prism. The angle of prism, that is basically 30. I think I had to make this opposite, not like this. I wanted this as 30, this as 60. That would be okay. Okay, so this will be then sine of a by 2. Angle of prism is basically 60, whole thing divided by 2. Yep, I just interchange the values or else it will not be a standard thing. So therefore, the refractive index will be 30 plus 60, 90. 90 by 2, 45. So it will be sine of 45 whole thing divided by 60 by 2 is 30. So sine 30. What is sine 45? It is 1 by root 2. What is sine 30? It is 1 by 2. So this will be root 2 and 2 on the top. So it will be root 2. So the refractive index approximately is 1.414. So that is the first answer. Okay, job done, sir. What about I and E? How do we do that? Well, there is a simple thing. Delta is I plus E minus A, and these both will be equal if this one is minimum. Oh, perfect. So what is the minimum deviation? Already given 30 degrees. What is I and E? Equal. So 2I minus angle of prism 60 degrees. Okay. So shift it over there. So 30 degrees plus 60 degrees is equal to 2 times of I. So 90 degrees is equal to 2 times of I. Therefore, I is nothing but 45 degrees. And E is also going to be 45 degrees. So incident angle and emergent angle both are 45 degrees. Got it? Yeah. Yes. Perfect. Perfect. Yeah. Cool. Clear. Shall we go ahead? Shall we go ahead? Yep. Great. Yes, Krishna, 45 degrees. Yes, 1.414, which is root 2. Yes. Oh, thank you also for reminding me to have some water. If they tell you there is a thin prism of 4 degrees having refractive index 1.5, find the deviation. How will you solve that question? Well, because the prism is thin, the deviation always is given by a into mu minus 1. That is the formula. If you forgot this, where it came? Right over here. A into mu minus 1. That's it. Just use it and directly you will get the answer. Angle of prism 4 degrees, mu 1.5 minus 1. 1.5 minus 1 is basically 0.5. 0.5 into 4, that's just 2 degrees. So the deviation is going to be 2 degrees. Such problems are very laddu problems or very simple problems. Then nothing is great in that thing. Okay, very straightforward questions. So I made you do some questions on prism. So now you know how to solve these questions as well. All right. Let's get to optical instruments, and this is the last part of this chapter. Direct questions may come in your NEET examination, and you don't even have to know the derivations as such. You just need to know the formula and the basic working, what is happening. That's it. Your job is done. So what's an optical instrument? An optical instrument is basically to see a bigger picture of the object. I am seeing through microscope a blood cell. I am seeing a tissue. I am seeing a plant cell. I am trying to see mitochondria. I am trying to see something else. I am trying to analyze some sample. So I will use a microscope or I will use a magnifying glass. That's an optical instrument. You become an astronomer or you become a space you go into space, or you become a space tourist, or you want to see a distant mountain. So you use binoculars or you use a telescope. So that is also an optical instrument. You are seeing a faraway object in an enlarged manner. So basically it magnifies, it enlarges it, and the final outcome should be virtual in nature. Makes sense? Or else imagine you are using a telescope and you are getting a real image. So you need to buy a cloth and you have to put it somewhere and you're like, oh sir, yes sir, I'm getting an image over here. I don't want to do that. I just want to see. Imagine you are using a binoculars and you are getting a real image. So you have to place the binoculars and then you have to hold the cloth. Oh, I'm getting an image over here. It will look stupid. Even imagine seeing a cell or a blood tissue or something on a cloth, on a real image. No. You want the image to be virtual, number one. Should it be erect or should it be inverted? I don't care really. Even if it is inverted, I'm okay with it. Just imagine I'm seeing a distant thing, and let's say a moon, or let's say a tissue, I get an inverted image. I'll be like, okay, fine. I will just look at it in the opposite way. I'm okay with it being inverted or it being erect. Both are fine with me. Next, it should be 100% magnified. That I can't compromise on. I don't want a diminished image. So that is what we are going to see. All right. Now there are, first of all, one main thing is there regarding something called as the magnification, magnifying power, which is way different than magnification. So let me define first what is the meaning of magnifying power. Magnifying power of an optical instrument. This magnifying power of an optical instrument is basically defined as the angle subtended by the image using the instrument, the whole thing divided by the angle subtended by the object without that instrument. What do I mean by this? Imagine this is the person observing a beautiful champa over here. Champa is very tall. So he is not using any optical instrument like telescope, microscope, anything, binoculars. So champa is subtending some angle over here. Let's say I call it theta naught. So this is basically theta naught, the angle subtended by this object without any optical instrument. But in the second scenario, what happens? This Pandu is using some kind of binoculars or something, I don't know, some optical instrument he is using. Okay, so because of which what happens is this particular Pandu sees a image of Champa maybe like this, then this will be the angle subtended by the image. It's not actually the object. This was the object, this is actually the image because of that optical instrument, maybe a spectacle, whatever. So that is basically your theta prime or theta 1 or whatever you want to call it. Theta prime, theta 1, theta, anything that you want to call. So this by this is called as the magnifying power. It's a ratio, it's unitless, dimensionless. It is not the same as magnification. Note, it is not the same as magnification. Is this clear? It's not the same as magnification. Is this absolutely clear? What is the meaning of magnifying power? So you might have seen on the microscope, it would be written 10x, 50x, 80x, 300x. What is that 300x, 80x? Magnifying power. So if there is a tissue of 1 millimeter, because of that microscope, it will look 300 times bigger. That means 300 millimeters. That's quite large. Got it? So that is the meaning of the word magnifying power. How many times angle-wise does it get expanded? Awesome. Now there are three instruments. One is the simple microscope. Then you have the compound microscope. And the last one, you have the telescope. Let me explain this to you via simple diagrams right over here. Why not? What exactly might be happening? So let's say a beam of light, and let's use a simple convex lens over here. Oh, not this one. Observe this now. This is a convex lens. We know the rays will converge. For a concave, it diverges. Obviously, using a concave lens is meaningless because if there is an object over here, imagine there is a penguin. I will see a smaller picture of the penguin. I don't want that. I want a bigger picture. So definitely, I will not use a concave lens. I will use a convex lens. But I don't want the image to be real because this side it is real in nature. So what I will do, I will make sure this is my magnifying glass. I am seeing through a magnifying glass. I am seeing this object. I will go closer to the object, or I will bring the object closer till it comes before the focus, not beyond, but before the focus. The moment I go before the focus, a very interesting thing happens. You can see that the image becomes virtual, it becomes enlarged, and it is also erect. That is a good advantage only for me. So I can see an enlarged image of that particular object. Are you able to see? So this is the functioning of a magnifying glass. The same diagram, but in a very boring way, has been mentioned over here. See this? This is an object, this is the image. It's virtual in nature. Can you see that? Virtual image, real object. Yep. Object, virtual image. Is this clear? But I have two options with me. Now, you might have heard about this human eye since you are biology students, that human eye is a very miraculous lens and it has got the power of accommodation. Means it can adjust its focal length, everything, depending on what are you concentrating on. If you are seeing a distant mountain, the things, the ciliary muscles will contract, expand, etc. and it will focus onto the distant mountain. I am seeing something very close, it will again focus itself on that closer object. But there is a limit till which it can accommodate depending on how well your eye is maintained. So one is called as the near point, the other is called as the far point. Near point is the closest distance till which your eyes can strain your ciliary muscles and can focus. I can see my hand now. I can see it now. Now I'm not able to focus. Now I'm not able to focus. It's looking blurred. So there is a near point, and usually for an average human being, it is 25 centimeters. Because whenever you want to see things clearly, what will you do? You will go close, right? You will not go, sir, I want to examine this sample. Push it far away. You are stupid then. If I want to examine a sample, you will bring it close. But you can't bring it too close. You will be like, okay, sir, I put it on my eye, sir. I can't see, sir. What is happening, sir? It's too close. Obviously, you have to place it at the near point. And your near point is 25 centimeters for an average adult. Correct? Got it? Similarly, the far point is usually infinity, means you can see a star. How far is a star? Infinitely far away. So you can see stars, that means your far point is infinity. But if you have a defective eye, then the far point can be 10 meters or 2 meters. There are some people, I can't see what teacher is writing on the board. That means the far point is not infinity, he has a defective eye. That can be corrected using lenses. Same thing can be corrected for a near point defect as well. Okay, fine. Now, if I want to see this penguin's image clearly, what will you do? Will you keep the penguin at the near point, or will you keep the penguin really far away? See, if you keep the penguin really far away, yeah, well, I have to focus. My eyes are a little less trained, okay, but it is far. Whereas if I keep it from my eyes, this is where my eye will be, this is where the magnifying glass will be, at 25 centimeters, very close, and I will see a big image. So I will try to keep it at the near point to get a very crisp, crystal clear image, magnified image as much as possible. So that kind of setup where the image is formed at the least least distance of distinct, that means clear vision, that is one setup. And the other setup is when I place the object such that the image is formed really far away point. The image is very, very far away. My eyes will be relaxed when I see far away. Some sunset I see, I'm relaxed. But I'm seeing some point on my nail. 5 hours. I will lose my mind. Yeah, because my eyes will be strained. Got it? So that is what the two arrangements are. Is this clear? Distinct vision, least distance of distinct vision arrangement where the image is at 25 centimeters approximately. That is called least distance of distinct vision arrangement. This one, when it is really, really far the image, that is usually called as normal vision. Normally, when you are seeing things are far away. So normal vision, your eyes are relaxed, at peace. So that it is normal vision. So in both the cases, the magnifying power has been defined. So let's have a look at the formulas as it is. You don't need the derivation. So the magnifying power is 1 plus d by f, where what is the d? What is the d? This is basically your d, my dear warriors. 25 centimeters or more. What is this? 25 centimeters. Is 25 centimeters given somewhere? No. So d is your least distance of distinct vision, which is approximately 25 centimeters for an average adult. It could be different for many of you. If you have a defective eye, it might be more. If it is very good, it might be even less. Okay, so that is your D. What is F? F is the focal length of that lens. So it is 1 plus D by F. This is for LDDV arrangement. This is when the image is at the near point, that is least distance of distinct vision. But if at all you decide to keep it very, very far away, this is your normal vision. That means the image is at infinity. The image is at infinity. So you can see it is d by f. No 1 plus d by f, it is just d by f. Is this clear? These are the two magnifying power formulas. Remember, magnifying power, I had defined this. So magnifying formula, when you are close, it is 1 plus d by f. When it is very, very far, then it is just d by f. These are the two things that you need to remember. Okay. Now, I'm not very satisfied with this. Let's say for example, if I use say a microscope, simple microscope of focal length 5 centimeter, what is the max and minimum magnifying power? What is the maximum and minimum magnifying power of that simple magnifying glass? The answer will be the magnifying power for normal vision, which is just d by f, d being 25, f being 5, will be 5x or 5 times. The magnifying power for least distance of distinct vision will be 1 plus d by f, which will be 1 plus 25 by 5, which is 1 plus 5, which is 6. So this is obviously the maximum, and this is basically the minimum. So when you're holding it very close, it is 6 times magnified. When you're holding it very far, normal vision, it is 5 times magnified. But this might not be enough for most of the cases. 5, 6 is a very small number of magnifying power. We need more values. So you will be like, let's use more lenses. And that is exactly what is done for a microscope. So this is basically the diagram for a compound microscope which uses two lenses, and the diagram is shown as here. The produces the final image which is enlarged as well as virtual. The first image is inverted, okay. The final image is inverted with respect to the original object, okay. So this is your basically compound microscope. Now let me see if I can somehow make that compound microscope for you. It's slightly difficult. This is a convex lens. I need one more convex lens. No, I can't do it over here. Sorry guys, I can't create that over here as of now. It's not allowing me. I can't create two lenses. I wish I was able to add two lenses. Then I would have been able to show it to you. Okay, anyways, I'll just show you here only what exactly is done. Hmm. There is a lens here, and there is an object which is placed. The rays from this particular object, the rays from this particular object, let's say they will go like this. Okay, they're going like this. So they are meeting over here. So definitely an inverted image is formed right over here. Definitely an inverted real and enlarged image is formed right over here because of this lens. Now you use one more lens right over here. Now you use one more lens right over here. This lens is such that this point or this image is before the focal length of this lens. By the way, this lens is also called as the objective lens. Reason being it is closer to the object. This lens is also called as the eyepiece lens or just the eyepiece because your eye is where the lens is. Yeah, and it's closer to the eye. That's why eyepiece. You see through that lens because the focal point of this lens is here, and the object, which is actually the previous guy's image, is before the focus. It will now make an enlarged image because of that. So you will probably see things going like this. Mhm. 1 second. Now I have to extend it backwards because it is virtual in nature. It is meeting over here. So I will see that the final image is formed somewhere over here. This is the final image. Whatever I showed over here was an intermediate image. This is the final image. Now this final image, as you can see, if it was here, it is below, so it is definitely again inverted. But you have to extend the rays, that means it is virtual in nature. And lastly, it is enlarged. So this is a two-stage magnification. First time it gets magnified here, second time it gets magnified here. So you get multiple magnifications. So because of which you get a finally, a big image right over here. I hope this is clear. I hope this is clear. Yes. Shall we go ahead? Shall we go ahead? Harry, first of all, I know your institute and I know how these kind of institutes work and trying to spam onto different channels. I know you guys have even gone to some big popular channels also and spam. So really, I don't care. Thank you so much. Don't spam. I'm just going to block you. Okay. Right. So moving on to the formula for the magnification. 1 second. Oops, I don't need to delete this. Yeah, this and this not needed. Okay. Right over here. Yeah. So the magnification formula that you get, yes, is right over here. So let me just write it over here. The total magnification is this one right over here, where what are these terms? D is your least distance of distinct vision, which is 25 centimeters for an average adult. F naught and Fe. F naught and Fe are basically the focal lengths of objective and eyepiece. FO is the focal length of objective. Fe is the focal length of the eyepiece. Lastly, you need something called as the distance between the two lenses, which is L. This is also called as the length of the tube of the microscope. So that is basically your L. So the magnifying power is given by length of the tube by focal length of the objective. Objective is basically this guy. L by FO multiplied by D by FE. What is D by FE? Least distance of distinct vision divided by FE. That's it. That is what it is. Very good. All right. And Bhargavan, let me also tell you that there are reasons for that, because I got spammers on some videos. See, these are the cheap tricks used by some of the teachers. And unfortunately, some good teachers also fall to this prey because of certain institutes. I don't know whether the teacher was involved or not, but some teachers or maybe some institutes use some cheap tricks going on to videos when you have left a channel, going to that particular video and commenting on every comment saying that, hey, you know what, I'm here now, you can watch this. Hey, you know what, I'm in this, I'm doing that. So these are the kind of tricks and stupid things which many people do, which is why, and they were not real students. I know real students, genuine students never do that. From some fake accounts create comment replies and suggesting students, hey, don't watch that, and spamming onto the existing teacher's class saying that, hey, this teacher is not teaching well, hey, this teacher is not doing that, hey, teacher is not doing this. This is what I don't like. Otherwise, we never do such things. We never had to make things private. So really, those students who actually comment such things on such videos, they are not even, first of all, real students. Number two, they are probably influenced by the institute or by the teacher. So really, I don't care about such people because they are not genuine students. I really only care about students. That's all. Only care about students. For me, what other teachers say, what they don't say, I really don't care, honestly. For me, students' lives matter. Okay. Moving on to the question, moving on to the next concept right over here. So magnifying power, yes, this is done. So they have just given an example. Imagine a microscope whose objective of the focal length has 1 centimeter focal length, and the eyepiece has a focal length of 2 centimeter. The length of the tube is 20 centimeters. Then what do? Length of the tube by FO, D by FE. Length of the tube is 20. Focal length of the objective 1. Then eyepiece has a focal length of 2 centimeters. D is 25. They have substituted. You can see this is a huge magnifying power, which is 250 times. If you compare it with our previous example of a simple microscope 5 and 6, that was very nominal. So my dear students, this is much larger, much larger. I hope this is clear. Yep, very good, awesomeness. Moving on to the last instrument, and that is the telescope. It is also very much similar to a microscope, just one small difference is there. I will tell you what the difference is. Imagine again, this is our objective focal lens. This is our objective lens. It's just that our object won't be very close. Unlike over here, it will be very far away. Like you will be seeing a moon, a mountain, or a star, or some galaxy. It's very far. So it's a very far away object, very far away object, and this particular very far away object will make an image right over here. When the object is very far, the image is formed at the focus. So this is an intermediate image, which is going to be real inverted, which is going to be real and inverted. Then you take another lens over here, which is obviously your eyepiece, and you ensure that the final image which is formed, this is your final image which is formed, is going to be inverted. It is going to be virtual, very similar ray diagram to the microscope, just that the object is very far, and it is what else is there? It is highly enlarged. It is definitely going to be enlarged. So this is what happens for a telescope, just that the object is really far, and this is where your eye is. Now again, same thing. This is the length of the tube, length of the tube of the telescope, length of the tube of the telescope. Perfect. This is basically the length of the tube of the telescope. Number two, basically, this is the focal length of the objective, focal length of the objective, right? Basically, reason being, when you have a very far away object, the rays will converge close to the focus. So that's why this becomes the focal length of the objective. This image is very close to the focal point of the eyepiece also, because of which the image gets highly enlarged. I'll tell you why. Just look at this. Just look at this. Imagine a very far away object. See, if you have a very far away object, see what is happening? The image is formed very close to the focus. And if the object is close to the focus, the image is highly enlarged. I hope you can see the image right over here. It is highly enlarged. So, if the object is close to the focus, the image is highly enlarged. And if the object is very far, the image is formed very close to the focus. So this characteristics is what we have used. Object is far, the image is formed at the focus, and the image becomes the object for the next lens. So if the object is very close to the focus, that means this becomes approximately the focal length of the eyepiece. Then the image is highly enlarged, and that is what exactly you want. So that is the reason why you will see that the length of the tube is FO plus FE in most of the telescopes, and that is what also would have been mentioned over here. Yes, as you can see, The length of the telescope is f naught plus fe. Can you see that? The length of the tube is f naught plus fe. So that is one thing. Last thing, the magnifying power is fo by fe. The magnifying power of a telescope is focal length of the objective by focal length of the eyepiece, which has just been mentioned right over here. That is something which you should again remember. Okay, so say for example, if you have an objective focal length of 25 centimeter or let's say 50 centimeters, eyepiece has a focal length of just let's say 0.5 centimeter. So 50 divided by 0.5, 5 cancels, it will become 100 times. So the magnifying power will be 100x. So you will see a very good clear image because it has got 100 times the magnifying power. That's how you calculate the magnifying power of the telescope. Okay, so that is what they have mentioned. And the last paragraph, they also tell about some additional things about the telescope regarding some considerations. You will see that the objective of a telescope, if you see a telescope, if we just even Google the image of a telescope, okay, let's say even just we see how a telescope looks like. Yep, look at this. Big objective, small eyepiece. Big objective, small eyepiece. Yes, can you see? Big objective, small eyepiece. Can you see that? See, the objective is so big, the eyepiece will be very, very small. The objective is very, very big. Can you see that? Objective is very big, the eyepiece is very small. Why the objective is very big? Why is the objective big? Because when you distant stars, moons, planets, galaxies, anything, celestial bodies, the light coming from them is very small. Now, we know this fact. If more light falls onto the lens, the image formed will be more clear. That's the reason why the diameter of the objective is very big, so it can take in more and more light to make a very clear image. Number one. Number two, the number two fact is that there is a phenomena called as a diffraction, which is deleted right now from the syllabus, which states that when you have a small hole, then the light which enters it spreads. Now that is an undesirable effect. Imagine the light is passing through a very small diameter, then it will spread, and the moment it spreads, it's going to cause undesirable effects. That's the reason why if you have a big diameter, then the light will converge very clearly, the image will be resolved properly, the image will be crisp, and the undesirable effects of diffraction are no longer there. So that is why they have mentioned that the diameters are very large. With large diameters, even the fainter objects can be observed. The resolving power or the ability to observe two objects distinctly, which are nearly in the same direction, also depends on the diameter of the objective. So that is the reason why you make the diameters very, very large. That is what has been mentioned over here. In more advanced telescope, they also use mirrors and other things. Modern telescopes, they use concave mirrors rather than a lens for the objective, and these type of telescopes, they are called as reflecting telescopes. That particular thing is not there in our syllabus. So the telescope images which I just showed it to you right over here, they need not have two lenses. Sometimes they even have mirrors, they even have prisms. So combination of even more lenses can happen. So those are modern day telescopes. Okay, that is something which has been mentioned. Chumma, they are told. Okay, they are like showing off. Hey, listen, modern day, many lenses are there. Hey, I'm not going to teach you. Hey, listen, there are mirrors also, but you are not going to study. So some show off has happened in this last paragraph, and they end it over here. So to summarize this particular chapter, we started off with reflection, which was angle of incidence is angle of reflection. Then we went to refraction, which is the bending of light. We saw Snell's law, which is sin I by sin R is refractive index, which is the ratio of the speed of lights. Then we saw a critical angle phenomena. When light goes from dense to rare, it bends away from the normal. So you have a limit on the angle of incidence called as the critical angle. Beyond that angle, the light internally reflects. Then we saw the mirror equation, which was 1 by v plus 1 by u is 1 by f. Focal length of a concave or convex mirror is r by 2. We also saw the sign conventions. Then we also saw lens formula, which was exactly same, just you have a minus sign. But the focal length given by the lens maker formula, which is mu minus 1, 1 by r1 minus 1 by r2. We also saw prisms and how deviation depends on the incident angle. The formula for deviation, which was I plus E minus A, R1 plus R2 is A, and for minimum deviation, it is sine A plus delta by 2 by sine A by 2. We also saw thin prisms. We also saw combination of lenses where the powers get added or the reciprocals of the focal lengths do get added, right? And finally, we ended the lecture with magnifying power, which is the angle subtended because of the instrument upon angle subtended by the object without the instrument. So the ratio of magnifying angles, yes. And we saw for a basically a single lens, it is 1 plus d by f or d by f, depending on whether you are holding it close or far away. For a microscope, L by f naught into d by fe. For a telescope, just f naught by fe. That is what we have seen. Dispersion is not there in NCERT, but they have just mentioned that dispersion is splitting of light. I can just show you what dispersion is right over here. Just let's get rid of this. Just imagine I take this prism, and instead of this, what if I use white light? Wow, it looks so nice, guys. I hope you can see. This white light has been, I don't know whether you can see it, it has been split into its constituent colors. Violet, indigo, blue, green, yellow, orange, red. Violet deflecting the most, red deflecting the least. This also means every color or every wavelength has its own unique refractive index. Violet having the highest refractive index because you can see violet has been deflected the most. Red having the least refractive index, that means it is deviated the least. It also shows that if you mix all these colors of Vibgyor, violet, indigos, blues, yellows, oranges, reds together, you see or perceive, the human brain perceives it as white color. So white is a mixture of all these colors together. And the best thing is I can also add multiple more prisms over here so that I can even spread it more. I hope you can see more and more refraction happening as we progress. Yeah, see, more and more refraction is happening as we progress, and more dispersion. Dispersion is basically where you split the light and we figure out what is it made of. White is made of all these colors, so that is basically dispersion. It's nothing but, splitting of light into its constituent colors. Awesome, right? So that is what it has been mentioned. So that's about it, and we are done. Okay, great, guys. I want all of you to put it up in the comments rated, because ray optics part 1 and part 2 is done from NCERT. Obviously, problem solving sessions will be there very, very soon. Thank you, Disha. Thank you, Krishna, for all the love. Madhi, thank you so much. Thank you so much. What is a Gherian telescope? Emperor, I'm not really sure of it. Maybe I'll have to figure it out. I'll do the same thing what you will do. I'll also Google. You will also Google, but maybe I'll understand it. I'll explain it to you if you want. Okay, cool. So thank you so much, and love to see you guys in the comments. Even if you are new or old student, please put it up and subscribe to the channel. And do not forget to like this video and also recommend this channel, because something really, really amazing is going to come up on Vedantu NEET English very soon on 28th of November, and that's hope. So meanwhile, Station 0 NEET Express is there. Today, Diksha ma'am's class, and then you have my class tomorrow. And before this, if you have missed any of the classes, do not forget to check out the biology classes as well. Okay. Thank you so much, guys. Bye-bye. Have a great time. Lovely, lovely day ahead. This was Captain Shreyas signing off.